Hi everyone. This video serves as an introduction to section 7.5 of our text, where we will be studying second order systems and mechanical applications. So the goal of this section is to apply the matrix methods we've been learning to investigate the oscillations of typical mass and spring systems having 2 or more degrees of freedom. And the examples chosen are to illustrate phenomena that are generally characteristic of complex mechanical systems. Now, the figure here shows 3 masses, M1, M2, and M3, that are connected to each other and to 2 walls by 4 indicated springs labeled K1 through K4. We're going to assume that the masses slide without friction and that each spring obeys Hooke's law, meaning its extension or compression X and force F of reaction are related by the formula F equals minus Kx for some constant K. We also assume that when the system is at equilibrium, none of the springs is stretched or compressed. So if the rightward displacements x1, x2, and x3 of our 3 masses from their respective equilibrium positions are all positive, then the first spring, K1, is stretched a distance of x1. The second spring, K2, is stretched the distance x2 minus x1. The third spring, K3, is stretched the distance x3 minus x2. And the fourth spring, K4, is compressed the distance x3. Now, therefore, if we combine Hooke's law, which told us that the force was equal to minus Kx, as well as Newton's law, which tells us that force is mass times acceleration, and we combine and we apply these laws to the 3 masses, it yields the following equations of motion. M1 x1 double prime equals minus K1 x1 plus K2 x2 minus x1. M2 x2 double prime equals minus K2 x2 minus x1 plus K3 x3 minus x2. And M3 x3 double prime equals minus K3 times x3 minus x2 minus K4 times x3. Notice on the left of the equal sign, that's Newton's law, where we have our force equal to mass times acceleration. Acceleration, of course, being our second derivative. And what we see on the right-hand side of the equal sign, this is where we're using Hooke's law to say that we could also describe this mass as that minus Kx. Now, we can write this system in matrix form, where we have on the left-hand side a diagonal 3 by 3 matrix whose entries down the diagonal are our masses M1, M2, M3, times our acceleration vector, or our vector containing all of our second derivatives. And then on the right-hand side, we have a matrix, a coefficient matrix containing all of the information about the springs, times our displacement vectors x1, x2, x3. And a simple matrix multiplication will verify that this is in fact equivalent to the system we have above. For shorthand notation, you will see that we're going to write this system as the matrix M times the vector x double prime equals the matrix capital K times our vector x. Just to give you a little more introduction into these matrices and vectors that you see here. Notice that vector x, again, the x1, x2, x3, we're going to call that the displacement vector. And that matrix M is our mass matrix. It's that diagonal matrix that has down the diagonal the values of the 3 masses. The matrix K is called the stiffness matrix. And recall once again that we can write this system in the form mx double prime equals kx. All right, we're going to start by considering a frictionless mechanical system. In a later video, we'll add friction to the mix, but in this video, we're only going to consider a frictionless mechanical system. And we're going to start with an observation about our mass matrix, that diagonal matrix M. Notice that the determinant of this matrix is just M1 times M2 times M3, which is non-zero since our masses are non-zero. And since the determinant of M is non-zero, that automatically tells us that M is invertible. So we get a homogeneous second order system, M x double prime equals Kx. And because M is invertible, we can solve for x double prime and say that x double prime is M inverse times Kx. And then just to simplify notation, we're going to write that as x double prime equals the matrix Ax, where A, of course, is the product M inverse K. Okay, so to seek a solution of our system, x double prime equals Ax, we substitute a trial solution of the form x equals v e to the alpha t, where v is a constant vector. And so if x is v e to the alpha t, we want the second derivative, we want x double prime. And so x double prime will be alpha squared v e to the alpha t. And we're going to substitute into our equation, our x double prime equals Ax. We're going to substitute in our formulas for x double prime, which was alpha squared v e to the alpha t. We have equals A, and we're going to substitute in for x v e to the alpha t. Now, because we can cancel the exponentials, those are always non-zero. So this implies that alpha squared v must equal AV. Hopefully you recognize an equation like this. Normally, instead of the alpha squared, we would have a lambda, but here we're looking at an eigenvector, eigenvalue equation, where we're saying that the vector v is an eigenvector of the matrix A with corresponding eigenvalue alpha squared. And therefore, our x equals v e to the alpha t will be a solution of our system if and only if alpha squared equals lambda is an eigenvalue of the matrix A with associated eigenvector x. Great. Now, as a remark, if this system, x double prime equals Ax, models a mechanical system, it's typical that the eigenvalues of A are negative real numbers. So -4, -9, -16, something like that, or -5, doesn't have to be a perfect square. And so if alpha squared equals lambda, if our eigenvalues are negative real numbers, then that tells us that alpha is plus or minus omega I. And so our general solution then of our differential equation of our system will be x equals the vector v times cosine of omega t plus I sine of omega t. This is just because if our eigenvalues are complex numbers, right, then recall from previous work that this is the form that our general solutions will take, cosine plus I sine. And notice that the value omega gives a natural frequency of the system. So in conclusion, Theorem 1 tells us about second order homogeneous linear systems. And here's what it says. If the n by n matrix A has distinct eigenvalues, negative omega 1 squared, negative omega 2 squared, so on and so forth, with associated eigenvectors v1, v2, so on and so forth, then a general solution of our system x double prime equals Ax is given by x of t will be the sum of these pieces, constant times cosine of omega t plus a constant times sine of omega t times a corresponding eigenvector, where the a and the b are just arbitrary constants. Now, in the special case of a non-repeated zero eigenvalue lambda naught with associated eigenvector v naught, the corresponding part of the general solution x naught will be a naught plus b naught t times the vector v naught. Great. Okay, so that's all for our introduction to this system. In the next video, we're going to work through a concrete example. Thanks, guys. Bye.